Hi, welcome to educator.com. We're going to be talking about regression today. So here's the big goal of this lesson. Basically, we want to set up a conceptual understanding of regression before we actually learn to calculate and find it. So today we're going to do just a brief review of linear equations. Then we're going to talk about the regression as the center line. Instead of a center point, like the mean, we're going to talk about a center line. And then we're going to talk about prediction and error. All right, first linear equations. So y equals mx plus b should be pretty familiar to a lot of you. Whenever we think of y equals mx plus b, y is sort of, you could think of this as the output, or f of x. X will be the sort of input, or often, whatever's on this horizontal axis, the x-axis. Now, B, we'll start with B, is the y-intercept. Another way you could think of the y-intercept is where x equals 0, what is B? Because x will be, here, right? And so anything where x is 0, that will mean that y will have to be somewhere on this y-axis, right? So that's what we mean by y-intercept. And then m is slope. And, slope, I think, is something pretty, everybody pretty much remembers. But just in case you don't, here's how we calculate slope. I'll put it down here. Slope is really the change of y over the change of x. So when we say change, we think of delta, right? The change of y over change of x. But a more common way people refer to it is rise over run. And when you think of rise, you think of going up vertically or down vertically, so the anti-rise, and then running is sort of more horizontal, right? So what is the rise over run? And that's what we think of as slope. And when we talk about rise over run, we really mean in the direction sort of to the positive direction is up and right, and the negative direction will be down or to the left. So you could think of rise over run as an indication of rate of change, how much x changes in relation to y, or vice versa. And so these are sort of the components of our linear equations. And every line, it doesn't matter what kind of, it doesn't matter, what the line looks like. Every line, every straight line has an equation, and from that equation you could figure out where at any x what the y is, at any y what the x is. If you have x, y, and the slope, you could figure out the intercept. If you have the intercept x and y, you could figure out the slope, right? So this is a really useful equation for us. Now, we're going to be trying to find a line that is the mean, that is the center of a bunch of data points. And in order to do that, we would have to find its equation, because the equation is sort of like the name for the line. But in statistics, we're going to use this exact same equation, but we're going to write it in a little bit different way. It's just convention. Nothing conceptual will change, but we're going to change it around just very, very slightly and superficially. The first thing we do is we talk about the y-intercept first. So in statistics, it's y equals b comes first. And it's the first b, so it's b sub 0, or b naught. And so instead of the y-intercept being added second, we start from the y-intercept. And then we add the slope times x. And notice that the slope, it's not called m anymore, it's called b sub 1. And so we have b sub 0, which is the y-intercept, same idea. and b sub 1, which is slope. Same idea as before, right? And so this is how we'll refer to things when we talk about the equation for the regression line. All right, so what do we mean by the center line? Well, if you think about a scatter of data, if you have a whole bunch of data, you want to think about a line that somehow like sort of cuts through the middle of all of these points, right? And so right now we could just roughly draw a line, right? And sort of try to make it cut through the center of all these points, right? But that's a very, very rough line. But in order to find what the equation of this line is, I can, as long as I just have two of the points on this line. For example, if I take this data point and this data point, I could find the equation of that line. Now, it's because by having two x's and two y's, a set of x and y and another set of x and y, I could calculate rise over run, and then from having slope and an x and y, I could calculate the y-intercept. Now, that's a really rough line, but because it just depends on which 2 points I pick. If I pick these 2 points, I'll get this line. But let's say I pick this point and this point. Then I would get an entirely different sort of line, right? And even more, moreover, if I pick this line and this line, this point and that point, I'll get an even more different line, right? And so the question is, which 2 points do you pick, right? It might not be good enough for us to just eyeball things because we're really not sure which 2 points to pick. Now, if you only had 2 data points, then life is easy, right? Like you could just use those 2. But usually we have more than 2 data points. So just eyeballing a rough line may not be good enough for us. But if push comes to shove and we only have 2 data points, we could manually find slope and intercept and find the equation of that line. All right, so let's talk about this regression as a center line instead of a center point. So here are some reasons for summarizing with a regression line. And notice that for all of these, I'm talking about scatter plots. So regression lines are really used for scatter plots. Here, what we want to do is we want to have some variable here. So here's my first variable, variable 1. And here's my second variable, variable 2. And we'd like to get a line that sort of describes the center of all of these points, all these cases, whatever the cases may be. Why would we want a line, right? Why not just a mean, right? Well, sometimes there's not enough info from just a point. If you just had a point, for instance, let's say this point is the mean of my x's and the mean of my y's, right? So that would be x bar, that's the mean of x's, and y bar, right? So let's say that's my center point. That point might not give us enough information about this whole distribution, right? Remember, we talked about how to summarize a distribution, and we want that trend. We don't just want a point. We would like a trend. And when there's not enough information from a point, it's useful to have a center line. Also, we want to find a summary that describes the relationship between the 2 variables. So it's not just enough to have a point. The point won't describe the relationship between the 2, but a line does. A line will tell you whether it's pointing, whether its slope is negative or positive. The line will tell you that kind of information that you would want from something like a trend. And so that relationship is actually really important to us, and we wouldn't get that information from just a point. The third reason that you would want to summarize with a regression line is that it's often helpful to use one variable to predict the other variable, right? And often, by convention, we would put whatever we feel is the predictor variable on the x-axis. So we may use this to predict this. So we may use someone's weight to predict their height, right? Or vice versa, right? In case of weight and height, it doesn't really matter which is the predictor. And really, predictor variables are by convention. They're not causal variables. They are just variables that that we use in order to predict a second variable. And that second variable is called the response variable. And so one thing that's important to know is that the predictor variable, by convention, by just tradition, goes on the x-axis. And the response variable is often portrayed on the y-axis. And so that sort of goes along with this idea of functions, right? That we put in x, and f of x, the function, will crunch out for us an output, right? And that's how we think of predictors. You put in the predictor, and it'll crunch out for you the response, right? A predicted response. Now, when we talk about predictions, those predictions lie on the regression line. So this regression line equals all of our predictions, right? And so this means that, oh, when we think x is, you know, let's say 27, then the prediction line shows us that y would be 180 or something like that, right? And so that all the predictions lie on the actual line. Now, notice that a lot of our points do not lie on the prediction line. And so there's a little bit of difference between the actual data and the predicted data. Now, here's the goal of regression, the goal of this line. Our wish and fundamental desire is to find this line that's the center. It describes sort of the middle of all these points, right? And if you want to think about what the center really means, it's really that all the distances on one side are balanced by all the distances on that side. It doesn't mean that it has to be a perfectly symmetrical distribution, right? It just means that the point in the middle has to be sort of equidistant to all of these lines and equidistant to all of these lines, right? Think about it as like a balance, right? It just has to balance each other out. All the distances have to balance each other out. So that's how I want you to think of it. Distances on one side of the line, right? Balance out all the distances on the other side of the line. So to show you here, here is one distance. Let's take this point. This is the distance, this is my y distance away from the line, right? And I need all of these distances to be balanced out by all of these distances. Right? And so that's the hope of this regression line. And here's a really long distance right here. Right? And so I need all of these distances to balance each other out. Now, how would you find such a line? Because that seems like a lot of work. We have to find a line and then find all the distances and then jiggle the line around and make sure all the distances are really perfectly evenly matched, right? That seems sort of hard. We'll actually learn to calculate the precise slope and intercept of this middle line, the regression line, by using the method of least squares. And that's going to be a beautiful shortcut for us so that we could actually find that line without having to do all that work. That's in the next lesson, though. All right, so let's pretend that I've just given you the beautiful regression line. I've just found it for you. Yay, right? So let's say here I show you servings of milk per year shown by age, right? So here on the x-axis, we have age, right? So when you're, when you're, I guess, like 25, you might drink less milk than when you're 15 or 10, right? And here is servings of milk. And I've already drawn for you this beautiful regression line. And if you traced it all the way up, it would intercept at 795. And if you looked at rise over run, it would be rise 22 and go to, instead of the right, go to the left by 1, right? So 22 over 1. And so here we have this nice line, and there's two ways you could use prediction. One is that you could use prediction in order to find data for, in order to predict data for x values that you already are in the range of. Here's what I mean. So we have data for a 12-year-old, right? And we have data for, let's say, a 28-year-old, right? If I wanted to predict somebody in between there, right? So I wanted to predict a 20-year-old's milk drinking, right? What I could do is I could just put 20 into my equation and find the predicted servings of milk, right? So I could just do 795 minus 22 times 20. And I could get my predicted servings of milk. Now, when you make a prediction, instead of calling it y, we're going to call it y hat. This little caret thing on top of the y, right? This is called interpolation. When you have a range of x's and you're finding something within that range of x, you're predicting something within that range of x's, right? Because, and you could think of it as it's in the boundaries, right? So staying within range of data. Because this is the data that I used in order to create my line, right? And if I stay within the range of my data, that's called interpolation. But if I go outside the range of my data, right, that's called extrapolation. For instance, we do not have data on 10-year-olds, right? We don't have data on 10-year-olds. Can I just make that up, right? Can I just pretend that I do, right? Can I find my predicted y for my for people who are 10 years old? Well, obviously I can from just using the equation of the line, right? That's not the hard part. It's easy to plug in 10, right? But the question is, can I actually do this? Is this sort of legal for me to do? The reason that this is a little bit, the reason why we separate these into two different ways of predicting is that extrapolation is actually a little bit more risky. More risky. Because you're going outside the boundaries of your data. Right? Because you're going outside of the boundaries of our data, we're not sure that our predictions are going to be as accurate. When we stay within the range of our data, it's a more safe bet because it's more similar to the data that we used in order to create the line, right? So there's interpolation and extrapolation, and what I need you to know is extrapolation is just a little bit more dangerous than interpolation, right? Because let's say we go all the way to 0 years of age, right? So infants who are born. Would it be true that they drink all these servings of milk? Well, they don't. Many of them drink infant formula or breast milk, right? So it would be wrong to say that infants who are 0 years old drink 795 servings of milk a year, right? Because that would just be wrong. So that's what I mean by extrapolation being a little bit more dangerous, more risky. Oh. All right. Now let's talk about errors in prediction. So even though we have this nice equation for the line, one problem is that the servings of milk per year that we predict, y hat, that's not always going to fit with our data. That's not always going to perfectly line up with our data. In fact, you could see here, there's a lot of jitter around the line. And that's called prediction error. So the prediction error is the real truth, whatever the truth is, and the difference between that real truth and our prediction, right? Now, whenever we have data, it's often from a sample, and we don't know what the real truth is. We only have a sample. And so often we want to know prediction error, but this is sort of a theoretical idea. It's the difference between the truth and our prediction, but we don't know what the truth is. But what we do have is we have our data. We have this sample of points, and so what we can find is not the real prediction error, but what we call the residual. After we've found the best middle line, then what we can find is the difference between our data and that line. And so that is called the residual. And this idea here, the distances between our actual y, the data, and our predicted y hat, that is called the residual. And so notice that we have a whole bunch of residuals. And here's the thing, because some of our data is greater than our predictions, and some of our data is less than our predictions, right? We have a whole bunch of positives and we have a whole bunch of negatives. And so the prediction line, the perfect middle line will actually have a balance of positives and negatives, right? And so if we added all of those positives up with all these negatives, and it's perfectly these are perfectly distant away from this distance is exactly equal to this distance, right? And these are positive and these are negative. When we add them all together, we get 0, right? And so the hope, the ideal, is that all the residuals on this side and all the residuals on this side add up to 0, right? Because that would mean that our line is truly in the middle of all these distances. All right, so that's called a residual. All right, let's do our first example. So this is the same data that we've been looking at. And the question is, what is the residual for milk drank by 24-year-olds? Well, since we're finding the residual, we know that the residual is really the data y, the y that we have, the difference between that and y hat, or the predicted y. So to put it in terms of our example, it's the actual servings of milk that 24-year-olds drink, the data that we have, subtract out the predicted servings of milk that 24-year-olds drink, right? So first things first, let's find how much milk 24-year-olds actually drink. So if we go to 24, I think this is our data point right there. And we could just eyeball what that point looks like to us. That looks like maybe 24 and 225 or so. That looks about 1/4 of this. And so we already have our y, 225, right? And so we just need to find y hat. In order to find y hat, all we have to do is put in 24 into this line regression equation. So y hat will equal 795 minus 22 times 24, right? And that will be our predicted y. Here I'm just going to bring up a blank Excel and just put in 795 minus 22 times 24. All right, and we get 267. So this equals 267. And so we have 225 minus 267. And that makes sense because our regression line is above our predicted, our predicted servings of milk is above our actual servings of milk from our data. And so we should get a negative number, right? This should be the negative distance, right? And so once again in Excel, I'm just going to put in 225 minus 267. And here I get negative 42. Negative 42. And so that's our residual for the milk drank by 24-year-olds. We're off by negative 42. All right, example 2. If a residual is large and negative, where is the point located with respect to the line? What does it mean for the residual to be negative? Well, we already had an example of the residual being negative. It means that the point is below the line and below on the y-axis, right? So just to draw some examples for you, if we have a line that looks like this, one idea might be that our residual is way down here, right? So it would be large and negative given the y hat and the y, right? Because the residual equals y minus y hat, right? Another example that I could draw for you is something like this. Even in this case, this would give us a large residual because, once again, our y hat is greater than our y, right? So if the residual is negative, so if the residual is less than 0, then it must mean that our y hat is greater than our y, right? So with respect to the line, the data point is below the line. And what does it mean for the residual to be negative? It means that our prediction is greater than our data point. All right, example 3. If somebody said that they had fit a line, fitting a line means finding that regression line. They had fit a line to a set of data points and all their residuals were positive, what would you say to them? Well, let's just think about this. So let's say we had some sort of line and all the residuals are positive. That would mean that every data point is somehow above this line because if they were below, that would be negative, right? And so could that ever be the case if we want our line to be in the middle of all these points? No, right? And so I would probably say to them, perhaps they made a mistake. They made some sort of error because half of their, roughly like half of their distances should be positive and roughly half should be negative, right? Sometimes you could have like, 2 small positive distances and 1 larger negative distance. And so it could just balance out like that. But you can't have all positive, nor can you have all negative. So I would say to them, your line is not in the middle of these points. Line, not in middle. So it's not a good regression line. All right. Example 4. Interpret the y-intercept of the regression line in the milk example. Does it make sense to extrapolate here? Well, one thing that you also need to know is here, the x-axis only goes from 10 to 30. But we really need to take it all the way out to, let's say, here's 5 and 0. And really what we mean is here. That's where that's the true y-intercept, because x has to be 0, right? Does it make sense to extrapolate here? Well, this would mean that when x is 0, right? When x is 0, then y would be 795. And let's think about what that means. When x is 0, age, right? Age would be 0. We're talking about newborns, right? Is it true that newborns drink 795 servings of milk? Well, we just talked about that. It doesn't make sense to extrapolate here because newborns are sort of a special case. They don't really drink milk. They drink breast milk and infant formula. And so because of that, it doesn't quite make sense to talk about newborns drinking milk yet. And so it doesn't quite make sense to extrapolate that way. And so newborns are sort of an exception. And, you know, presumably this line will go on and on and on. And there will be a point where it crosses the x-axis, right? So this is the x-intercept when y equals 0. But it may not make sense to extrapolate there either, just because at a certain point it might the servings of milk might go into negative, right? And that doesn't make sense in our data, in our example. So it doesn't quite make sense to extrapolate really beyond the confines of our data. All right, so that's a conceptual understanding of regression. Hope to see you again for calculating regression next time on educator.com.